So we have this question here. It was also sent by the UNEB 2020. Anyway, it says the diagram below shows a cone of radius L and height h in which a cylinder of radius x is inscribed. Inscribed means that something is inside something. So now the cylinder was inscribed into the cone. So see that the height of the cone is h, the height of the cylinder is h prime. The radius of the cylinder is x, then the radius of the cone is a. So that then let's express h prime, height of the cylinder in terms of x, a, and h. Then show that b prime is equal to 4/9b, where b prime is the greatest volume of the cylinder that can be inscribed in a given cone of volume v. So we say this topic is falling under differentiation, applications of differentiation. Whenever you hear about greatest something or maximum. So you cover differentiation, you can go to the playlist of this channel or my channel, then you swipe downwards or downwards, you see there differentiation as the whole topic, where you have more examples like these ones here. So now here to get part A, express h prime in terms of x, a, and h. They are going to use similarity. Similarity works if we have two similar figures. So those can be having a triangle and a triangle, the same shape, but the size is different. Now here is that I can't use similarity here because this is a cylinder and this is a cone. So but if I bisect this into two, this will be dividing. If like this, then I cut it in a cross section of that. Then the half of the cross section, then I will be creating a right angle triangle. So if I do that, this is what happens. So if you have to divide it into two, I'm assuming that now this is the cone. So this is now the part of the cone. If I divide it into two, if I divide this cone into, remember this is just the base, it's flat, but just this is annexed to give you the illustration. So now this is going to be my cylinder here. So remember, if I divide this into two, then even my cylinder is going to be divided into two equal parts, like that. So I'm showing that this is now my simple cone, this cylinder inside the cone is we have bisected. And you know now, from here up to here, it will be the volume of the, now this is the middle part. So from here up to here, it will be the volume, the radius of this cone A. Then from here up to here, it's going to be x. So this is going to be x. Or from here up to here, it's going to be x. Remember, from here up to here is the same as from there up to there. Now, you start here. I've created two similar figures. You see this, and then the big one. So there I can use similarity. But because I want it in terms of, I want to express h prime in terms of h, there I'm going to use the heights. So the height of this big triangle from here up to here, down, that is h, will be the volume, and then it will be the height of the cone from here up to here. This is going to be the height of the triangle we cut out like this one. Now, because this one is having inside, now I also need the height of this small triangle, but I know that from here up to here, from here up to here is the height of the cylinder. So meaning I can get this height also. So if from here up to here is h, and from here to here is h prime, it means that this one, I get this minus this. It will be h minus h prime. So that will be the height from there up there. So there, so now we have, this is similar to this. So this is the small, this one is the big. So there we use that similarity. So using similarity, now there are many ways you can say big over small over big. So it's up to you. So I'm going to say now the big height over the big base. Then I say the small height over the small base, as simple as that. Or you can say the small over the big. It's up to you. So from there, I'm going to say big height over, now you can say big radius over big radius. It's going to be equal to small height over small radius. So you make sure that if you have big height here, you have small height. Big radius, small radius. So the big height, all the radius here in terms, I'm using in terms of the cylinder and then the base. Or you can say over, because we are doing the triangle, let us just say base, so that people can see that we are dealing with bases of the two triangles we created. So big base over small base, so that people can able to see the bases. So you can see that the big height from here to here is h of the big triangle over a equal to the small height. So that our small height of this triangle, because it's the one which is similar to this big one, it is h minus over the small base. The small base is this, which is x. So when I cross multiply here, you can able to see I'm having hx over a equal to h minus h prime. So when I take this inside and bring this side, so that my h prime will be now h minus xh over a. And so I have expressed h prime in terms of h, x, and a. So that's what we had to do for part A. Then part B, they want us to show that the volume of the volume I mean the greatest volume of the cylinder is equal to 4/9 the volume of the cone. Then the volume of the cone, the volume of the cone is given by V equal to, because the volume of the cone is V. So volume of the cone is given by a third pi r squared h. So it's a third pi, now the radius of the cone, which is r. So here our radius of the cone, this is going to be a squared. Then the height of that cone, so that it's h. This is the volume of the cone. Then I come to the volume of cylinder. You know that the volume of the cylinder is pi r squared h. So the volume of our cylinder is going to be pi r squared h. But our radius, is that the radius of the cylinder is x, but we are squaring it. Then our height is h prime. The height of the cylinder is h prime there. But we have this, so my VL is going to be pi x squared into my h. Now the height of the cylinder, which is now h minus xh over a, which when I open brackets, I have VL equal to pi x squared h minus pi x cubed h over a. Now, because we want the greatest volume of the cylinder, we differentiate this. Now you can see that we are going to be varying with the radius. So from there now I see now the V L, the x is going to be now, when you differentiate this, we say you lower the power, reduce the power by 1, you get 2 pi xh minus 3 pi x squared. When I differentiate this, I lower this power, that's where I'm getting the 3. I reduce this by 1 h over a. Now this h, I mean pi, x, and a, now those ones treat them as constants, because we are saying now the volume is valued with the radius x. That's why now these ones, for them, we treat them as constant. But know that for greatest volume, but for greatest volume, we say always that the v, the l, the x is always equal to 0. So meaning 2 pi xh minus 3 pi x squared h over a is going to be equal to 0. So now we give the reasons there. You can go and list them. So now it's that what is common, we have pi xh is common. So pi xh, when I factorize it here, I have 2 minus pi xh. So here I'm in with 3x over f equaling to 0. So either this pi xh is 0 or 2 minus 3 over x is 0. Now, if you want the maximum volume, it means that now x can't be 0 and h can't be 0, because these are volumes of, this x is the radius of the cylinder, h is the radius of the cone. So these two can't be 0 if you are looking for maximum. So, and pi for it is a constant which we know, which is 3.1 for something. So this one now, all of this can't be 0. It means that the only option which is 0 is this. So see that now 2 minus 3 over 8x is 0. So from there, that our x is going to be 2a the whole over 3. So now that is the value of x for the greatest volume. Now, in most cases, we are required to show that that is going to be the value of the radius, which is going to give us the greatest volume. How do we do that? You can use either the second derivative test. We usually now this is the second time. Then we put in this value of x to see if it's good for greatest volume. Then the v l over x squared, the second derivative of this, it should be less than 0. In simple terms, it should be negative. So now we share this the second time. So now our dv squared vl over the x squared will be, now this one, I'll be adding 2 pi h, then minus, then if this I get 6 pi x h, the whole over a. So it is substituting when x is equal to 2a over 3, so now our dvl over the x squared is going to be now 2 pi h minus 6 pi over a. Our x is 2a over 3 into h. Now you can easily see this one will cancel, and then this will give us, you see, now when I put in my x here for the second derivative, now I have, yes, when I'm running this right now, I put in my x here, x is equal to 2a. So when I put in my x is equal to 2a, so now this one cancels by 3 here, then by 3 I will have 2. So start now, this will give us, this is 2 pi h, this is b, 4 pi h, which is negative 2 pi h, which is now less than 0, implying that now therefore this one is the radius. It's going to be giving us the maximum. Now, the maximum radius, this is what we call the second derivative test. Let me put it there, second derivative test. Simple as that. It's negative. That's why it says that. So meaning it's the value of the radius at maximum volume. So now, you see now, the volume. Now we say that this volume VL equaling to pi x squared into h minus x h over a. Now we say when we are at maximum, then it becomes V prime. So now this volume is going to be V now prime equaling to pi. Now I have my x squared. What is my x squared? I square now this 2a over 3, the whole square, into now h minus x. 2a over 3, then times h over a. So this one is going to simplify to that. And this will be now giving us b prime, will be giving us 5. So it's going to be 4a squared over 9. We square this, we get this. Don't forget we square 2, we get 4, we square a, we get a squared. When we square 3, we get 9. Now here is that we are having h minus 2 over 3h, which we can easily simplify, multiply and b. Now, you see that our proof, we have 4 over 9. So let me prove out 4 over 9. 4 over 9 into now, you see here, n 4 over 9 pi. Here we are made with a pi, here a squared. Then when we simplify the whole of this, h minus 2/3, which will be made with h over 3. Now you can able see that the whole of this here, the one which is giving us this there. And so now our big line now is going to be now 4 over 9. The whole of this is b. From here, I think you see third is the thing which we have there. So which I can able take as this. You want that, I can now write it as this. This is the volume of the cone which we wanted to put there. So the whole of this is giving us, the whole of this is yielding h over 3. Which when we multiply with this, we get that, then we factorize out, and then we remove this. That we get now pi a squared times h over 3. That's what we get, and that's how we get our proof out. So that's it, members. You can, some people skip the second derivative test because anyway, but for formality, we have to show that the maximum volume is going to be good like that. So don't forget to subscribe to the channel. Then you can go to praise, you can change the part of the video the way you want. So that's it. I wish you well.